So here is an exam question for 2016. And the question is regarding the resolved motion rate controller, which is universally used in robotic systems when we know what the desired trajectory is, and it can then be used to ensure that the endpoint of a robotic arm actually follows the desired trajectory. And the question is going to be just, who came up with this, and then describe basically under which mathematical conditions the resolved motion rate controller is capable of controlling a robotic system, and algorithmic steps performed by the control. So this thing was basically invented by Whitney in 1972, and the way it works really is as follows, right? So it all relies on the fact that we can use the inverse Jacobian matrix in order to get a small change in the control angle, if it's a Revolut robot, if it's in the control signal anyway, given a small change in end effector position. So it all basically, one of the main aspects of this design is the fact that we can calculate the inverse Jacobian of our system. So what we need to do then with our system is first calculate the forward dynamics, calculate the Jacobian matrix, and then make sure that we can calculate the inverse. And in other words, if the system won't work, we can't use this if we can't calculate the inverse Jacobian matrix, which means the Jacobian matrix has got to have full rank. So that's the first thing from a mathematical perspective. So how does this thing actually work? Well, basically, the way it works is that we know that if we've got an arm which is set by configuration Q, and Q is quite often in a Revolut robot, it's going to be the joint angles. If we've got Q, which is, let's say, the angles, and we know everything about the linkages, we can calculate the forward kinematics and calculate the end effector position X. Right. So that's clear. We've got Q, and then we can calculate X. And generally speaking, when we consider this system, it will be set up such that at any particular time it's got a value of Q and a corresponding value of X. So if we've got a value of X, if we give the thing a very tiny displacement, XD, a very tiny displacement away from where we actually are at X, this leads to a tiny little delta X value, right? And this is this kind of thing that you can then feed into the Jacobian matrix in order to get a little tiny delta Q value. So at the small little tiny change in the displacement that we want, we can use the Jacobian matrix to calculate the small tiny change in the configuration that we want. And then what we can do is we can then basically apply this little tiny change in the joint or the parameters to control the input of the system to move it from Q to Q plus delta Q, right? And we end up with a small extra Q value going into the system in this way, and this gives the new Q value. And having got the Q value, of course, what we can do is we can then calculate using forward dynamics what the corresponding X value is. So the system's doing its thing anyway, but we can calculate the small change in X. Now, if the D that we're actually giving it is the actual desired value of X, what we can then do is say, well, if we're already at X, of course, there will be no difference between the two, so it'll have reached equilibrium. But if we then very slowly change XD, such that there's always going to be a little bit of a difference between what the system's actually predicting and what we want it to be, what it does then is it calculates a small delta X, because the difference between these is going to be a small delta X. And given the small delta X, we calculate the small delta Q that we need, we apply the small delta Q to the system, and of course it then moves appropriately through the queue. That system works fine, providing, like I said, we can calculate the Jacobian matrix.